Okay, welcome everybody for today's talk. So today we have the pleasure to receive here Felix Hernandez from USP São Paulo to give a brief introduction about Felix's career. Felix had his bachelor degree in Costa Rica, Universidade de Costa Rica. He did his master and his PhD at Unicamp in Campinas. During the PhD, he had 1 year abroad at Universidad Dortmund with the Professor Manfred Bayer. He had some visiting professor positions in Rice University, University of Michigan. He had a postdoc at USP, a postdoc at CNPen. He visited many places throughout his career: IBM, Zurich, McGill University in Canada, the Grenoble High Magnetic Field Laboratory, CNPen, and so on. And Felix is a professor at USP since 2009, if I got it correctly. So, okay, this is a brief introduction. So welcome, Felix, and feel free to present your talk. If there's any questions in the audience, I'll interrupt you briefly to ask you the question, okay?
Okay, thank you, Gerson, for the introduction, and thank you for the invitation. In this talk, I want to present this combination between topology and chirality of phonons, mostly the results published in this PRL from 2022 and Science Advances 2023. This work was a collaboration between many groups, the University of São Paulo, Rice University, theory from Texas, University of Texas at Austin, and Northeastern and MIT. And samples were grown here in Brazil, in INPE. And the instrumentation for high magnetic field was developed in Japan in Yokohama National University and Tohoku University. And this work was funded by FAPESP, CNPq, and NSF-ERMSEC. One important point in my presentation is to give you the link for my group is portal.if.usp.br/terahertz, where we have some opportunities for students, fellowship for doutorado direto, FAPESP, and postdoc. So let's start first with the idea of chirality. So chirality is very important property in nature. It refers to the asymmetry between an object and its mirror image. The word chirality comes from hand in Greek, and the hands are the most traditional object, which is chiral, right? So left hand and right hand. In this talk, I will use chirality to chirality of phonons in the sense of a left and right-handed circular polarization. So you see like this. So when the phonon is polarized circularly, I will say that the phonon is chiral. And also in this talk, I will only show results for transverse optical phonons, which can couple to light. Here I have an example of TO phonon in lead telluride, which is one of the materials that I want to present today. And here you can see that these red and blue spheres, in the absence of magnetic field, oscillate in this TO phonon mode in a linear direction. So they move oppositely, one towards the other, like this, along a linear direction. However, when you apply perpendicular magnetic field, then these ions perform these circular orbits, which are also in opposite senses. And then this is a chiral phonon for lead telluride. One of the first observations of circular polarized phonon states is this paper from 76, where people observed that the phonon modes split with the application of a magnetic field, right? So one important difference here is that this material is a paramagnetic material. So the splitting is very large because of the magnetism of the material. In my talk, I will only show you materials that are non-magnetic. People also knew that there are some effects, Morphic effects in the crystal symmetries that lead to this kind of effect, giving chirality to the phonons. So the story of chiral phonons in non-magnetic materials is very new. This is the first paper in Science 2018 for rotating modes. So if we return here, you can see that this mode rotates but also propagates, right? It moves like this, rotating and propagating. So these modes here are only rotating modes. This is because the samples are two-dimensional materials, and then the phonon is confined in only one layer of the material. However, this publication was very important because at that time it was not clear if collective modes like phonons can have chirality. Here I highlight one part of the text. It says that chiral fermions sorry, not this one here. The outstanding question is whether bosonic collective excitations, such as phonons, can attain chirality. So there was some asymmetry between the knowledge of chirality of fermions and chirality of bosons. For chirality of fermions, the knowledge is very mature. We all know that chiral fermions are an important part of topology, but chiral bosons were still unknown, at least not experimentally detected. And this is the first paper that will present the observation of chiral phonons in 2018 for rotating modes. For propagating modes, the experimental observations are more recent. Here you can see truly chiral phonons in mercury sulfide. So here you can see that people use circular polarized Raman scattering, and there is also here a shift between left and right-handed circular chiral phonons. Okay. Even more recently, last year in Nature, they observed that chiral phonons can be found in quartz and be probed by X-rays. So far, this field was mostly focused in finding what kind of materials can host chiral phonons. Okay, so this was the first idea in this area. What kind of materials can host chiral phonons? What are the symmetries of these chiral phonons? Are rotating, propagating? You can see here that there is some kind of what is the name for this? I forgot. There is some kind of controversy in this title. They choose truly chiral phonons as to make a point against the phonons that are just rotating. In their case, they explain that chirality of phonons can only exist if you have propagating phonons, not just rotating. So in the field, there was a large controversy, which kind of phonons are truly chiral and what kind of materials can host chiral phonons. However, this controversy, of course, is very important for the field to grow and also attract a lot of attention from many groups. Okay, so let's come back here. And why a chiral phonon is important? What can a chiral phonon do? In this case, I'm showing you here a paper from Physical Review Research where they propose, this is a theoretical paper, they propose that giant effective magnetic fields can be generated from optically driven chiral phonons. So the idea is that you have a paramagnet, and then you shine terahertz pulses with a given frequency determined by the phonon absorption. And then, depending on the fluence, the energy of these pulses divided by the area, you will have a very large effective magnetic field. In this case, for example, they calculate that if you use 40 millijoules per square centimeter, then you can have an internal magnetic field in this material in the order of 100 Tesla. So imagine that you have this material, and then the phonon, the propagating phonon, can be triggered using light, and the phonon behaves like a coil inside the material. It will propagate, and then it will induce this very large magnetic field. Okay, so experimental realization was performed and published here in Science last year. You can see here large effective magnetic fields from chiral phonons in rare earth halides from the group of Hanyu in rice. And the effect is not so large, but it's quite large. The problem is that you cannot really experimentally produce this huge fluences. Here 40 you see, but then in the experiment is much lower, less than 1. However, even with a smaller fluence, you can produce a peak magnetic field in the order of 1 Tesla, which is still quite a large, very, very large internal magnetic field created by the action of this chiral phonon. Another example here of an application in this paper, they create a device where you can have a chiral phonon activated spin-Seebeck effect, and in this case they choose perovskite. Is a two-dimensional layer hybrid organic inorganic perovskite to replace this ferromagnetic material. So in the traditional spin-Seebeck effect, you need to apply a magnetic field, you need a ferromagnetic material, but when you use chiral phonons, you don't need a magnetic material. This is a non-magnetic chiral material, and also you don't need the external magnetic field. So you can see that with the use of chiral phonons, you can produce a much simpler device where you don't need to apply external magnetic field. Okay, so the point that I want to focus in my talk is phonon magnetic moment. Phonon magnetic moment, there was a large controversy and difference between theory and experimental results. In theory, we will see that the prediction shows that phonon magnetic moment should be very small, but in the experiments, the result was a very large phonon magnetic moment. So I want to discuss first the theory. Here is one of the first papers, Physical Review Materials, the 2019, orbital magnetic moment of phonons. And then they show that if you consider only orbital magnetic moment of phonons, then, for example, for lead telluride, which is one of the materials I want to show you today, the phonon magnetic moment in these units here of delta omega divided by the frequency of the phonon, even at such large external magnetic fields of 50 Tesla, should be very small splitting here, 0.0006. However, in experiment, for example, in this Dirac semimetal cadmium arsenide, people observe 2.7 times Bohr magneton, so huge phonon magnetic moment, orders of magnitude different from the prediction only taking into account orbital magnetic moment. So what is the difference here? The difference here is that in this material, they have a crossing between cyclotron resonance of carriers and the resonance of the phonon mode. So cyclotron resonance of carriers can be tuned by the application of the magnetic field. The phonon frequency also changes with magnetic field, but much more slower. So there will be a magnetic field where they will cross. And they say that when you have this crossing between cyclotron resonance of carriers and phonon resonance, then you have an enhancement of the phonon magnetic moment, given this large effective result. Here I put the most important result of this paper. Then you have here, this is the frequency of the phonon, and then you increase the magnetic field. And when you have the crossing between the cyclotron resonance and the phonon mode, then at a given field, then you have this enhancement. Okay, so this idea, I choose this paper because this idea is very related to the point that I want to show you here, which is the interaction between carriers and phonons resulting in large phonon magnetic moment. Okay, here more examples: chiral phonons plus electrons. Some other papers, this is a PRL from 2021, phonon magnetic moment from electronic topological magnetization. Another PRL from 2023, gate tunable phonon magnetic moment in bilayer graphene. From last year, Physical Review B letters, electron magnetic moment of transient chiral phonons. So what all these papers have in common is what is the effect of electrons, and carriers can be holes also, but let's say electrons. What is the effect of electrons in the chirality of phonons, and how this effect, how this interplay result in large magnetic moments. So the idea of these publications was to, let's say, correct previous theoretical predictions, saying that phonon magnetic moment should be small, and to try to explain the recent experimental results. Okay, so the system that I want to use to demonstrate the relation between chirality and topology is this topological crystalline insulator, which consists of lead, tin, and telluride. We study epitaxial films. It means that those films are grown by molecular beam epitaxy. And why this material? So this material is very interesting, first because the transverse optical phonon lies in the terahertz frequency range. It means that it can be accessible with current instrumentation using terahertz time domain spectroscopy. Also, this system suffers structural transition with temperature. So the frequency of this phonon becomes lower with decreasing temperature. And this is because the crystalline structure changes from cubic to rhomboedral, like this one, at a given temperature that we will call Tc. So there is a critical temperature where the crystal transforms like this, and then it enters a ferroelectric phase. So this material is ferroelectric below Tc. But more and most important, the gap decreases when you increase tin concentration, here X, right? When you increase tin concentration, the gap decreases until it reaches this point when it closes around 0.3, and then the gap opens again but inverts, And in this inverted phase, we have the topological crystalline insulator phase. It depends, this point depends on temperature. You can see for room temperature is much higher, but we will make all our experiments close to this point. So here these crosses are our samples, one in the trivial phase and two in the topological phase. Okay, this is the experiment. It's called terahertz time domain spectroscopy. In this experiment, we use the generation of terahertz pulses with pulse laser. So we use two pulse lasers, one for generation and one for detection. The laser for generation must have very high power, and then you shine this laser in a zinc telluride crystal, and you will have the emission of a terahertz pulse. In practice, all this experimental part with terahertz pulse will be closed in a box because humidity absorbs many frequencies in the terahertz range, and then you need to keep all this experimental setup in a porch box without humidity. So we use parabolic mirrors like this. So these mirrors, this one collimates the light and make it here parallel, and this one here focus the terahertz pulse in the sample. In this case, we are using transmission geometry, so the light goes through the sample and then is collected by this parabolic mirror and goes here to this detection part of the setup. And the second detection pulse follows a different path. The most important difference here is that we have a delay, mechanical delayed stage. So this part here can be adjusted, and like this you can change the delay between this terahertz pulse and the laser pulse arriving at the second crystal. And like this you can map the transmitted electric field, right? If you have, for example, this is the waveform of the incident electric field of the light of the terahertz pulse, you can see like this in time, then you can also measure the transmitted electric field of the light. You can see that there are some different oscillations here and here. So it means that the electric field of the light is modified by the sample, right? One very, very important point here is that terahertz time domain spectroscopy allows you to measure the electric field, not the intensity. For example, when you measure photoluminescence or other techniques that that measure intensity, you cannot collect the total or the electric field, the transmitted electric field. And because we can measure amplitude and phase of the transmitted electric field, we can calculate the complex refraction index, and as I will show you in a few minutes. Okay, for the experiment with magnetic field, we use very, very high fields up to 30 Tesla in a special setup called Rambo. And Rambo means Rise Advanced Magnet with Broadband Optics. So in this case, there is here a pulse magnetic field. It's not possible to have a constant 30 Tesla, only pulse. And here there is a cryostat. And in this cryostat, we have this tube, and the sample is here connected to the cryostat, but fixed here in the center of the coil. So like this, we can perform the same experiment in transmission. You can see here the light comes like this. Incoming terahertz radiation is transmitted through the sample and then goes here to the detection. Okay, so the scheme is a bit different because there is no time to move a mechanical delayed stage. We have here the pulse magnetic field, and we have here the sequence of light pulses. And for each light pulse, we will have a measurement at a different magnetic field. For example, this is a magnetic field pulse of 30 Tesla. So this light pulse will measure something like 3 Tesla. This one here will measure something like 23 Tesla. And this one here will measure 30 Tesla. So each is a technique that depends in single shot detection, only one shot of light for different magnetic fields. The detection is made with a camera, so we collect all the time points. The data is collected in a camera, so only at the same instant, instead of collecting point by point the waveform of the electric field. This is very difficult to do. The discharge necessary to produce 30 Tesla is very large. You need quite a big capacitor bank to give this discharge. And the problem is that since you can only use one single shot of light, then the signal to noise ratio is very low. So you need to repeat, for example, each configuration something like 50 times. Every data point is collected 50 times in order to have some good signal to noise ratio. Okay, so I want to show you here some example. Maybe if you never use terahertz time domain spectroscopy, an example for phonons. How do you see phonons in this kind of experiment? Here I'm using some figures from masters from my student that you can find in this link. So we use, first you need to measure the reference, right? The reference here is this black line. The reference means if you have a sample, for example, with a substrate, you measure only the substrate. If the sample doesn't have a substrate, then you need to transmit the light only through the air. In this case, I'm showing this mineral clinochlor. So it's like a small rock. It's a van der Waals mineral that we start to study recently. And then reference here, since there is no substrate, it's a natural mineral, then we only measure the air, right? And the blue one is the light transmitted through the sample to this clinochlor, right? You can see that there is a shift in the phase. This is because sample, of course, has a different refractive index. And also there is some modification in this time domain. What we do now is to apply Fourier transform. So the Fourier transform of the reference is this black line. It shows you all the frequencies contained in the incident pulse. So this pulse, right, has all these frequencies from 0 to 2 terahertz. This is our experimental window. Maximum is more or less like 0.6 terahertz. And when you have the sample, then you can see that almost doesn't change, but there is a frequency that is absorbed here. There is a very sharp dip, more or less at 1.1 terahertz. And if you then divide the electric field through the sample and through the reference, you can calculate something called transmittance. And from transmittance, here T, you can calculate then absorbance. And here you can see that there is a very nice peak corresponding to a phonon in this material. And also from this measurement, only from this data, you can calculate refraction index, which is this complex refractive index. One part, a real part, is the refraction index like this, and imaginary part is extinction coefficient, which gives you absorption. So there are some other techniques that allows you to also to obtain real and imaginary part. However, using some tricks, and in this case, this is only experimental. We are not using any equation to calculate, for example, a Kramer's chronic relation between real and imaginary parts. We can directly obtain the refractive index and also the absorption at the same time in the same measurement. Also, for other applications, you can calculate, for example, optical conductivity, which means the conductivity of the sample as a function of frequency. And you can perform, for example, the same experiments that you do in electronic transport, but without electrical contacts, only using the electric field of the light. Okay, so let's return here to the chiral phonons. So first, I want to show you the situation when x equals 0, meaning lead telluride, and we published this PRL that we call magnetic control of soft chiral phonons. Okay, as function of temperature of the TO phonon, we can see here real part of conductivity, and we see that with decreasing temperature, the phonon peak, like in this example that I show you, right? The phonon peak moves to lower frequency. Oops. From here, almost room temperature to 25 K, the phonon becomes narrower, but also more important for our application, it moves to lower frequency. Here there is a fitting of the frequency of the phonon as function of temperature. This model includes anharmonicity. Phonon modes in TO modes in this material are strongly anharmonic, and this is because this is why this material is very important for thermoelectric applications. So in this case, lead telluride is not ferroelectric. The phonon mode only decreases. As you can see here, frequency only decreases, but there is no turning point. You don't see it. It can become ferroelectric. Okay, let's keep that point in mind. We will compare later. So here I show you the same thing, but now I combine the linear components of the measurement in left-handed and right-handed. So here in the left, I have we have dash lines for 0 Tesla, solid lights are 9 Tesla, different temperatures. These three curves are the curves that I showed you before. Let's come back here. So these three curves here are these three here, right? But you can see two important differences. First, left and right have different height, right? At the same temperature. This one has this, and this one is much taller, right? So there is a very strong difference in height. This difference means that you have different absorption of circular polarized light. Okay, so that means that we have magnetic circular dichroism, right? This is the meaning of magnetic circular dichroism is a difference in absorption between light with different handedness, left or right. But this difference is much stronger with magnetic field, right? At 0 Tesla, there is no difference, 9 Tesla, is a large difference, right? So what we have is magnetic circular dichroism. And if we plot this MCD as functional temperature, you can see that it increases with a decrease in temperature, as we can see here. This for high temperature is more or less the same. For low temperature, there is a large difference. So more or less 30% MCD we can obtain for lead telluride. Another important point is that the dashed line and solid lines are shift. They are not centered. You can see this one is shift here to higher frequency. This one also shift to higher frequency, but not that strong as this one, right? And this is the result of the phonon magnetic moment. If we plot this phonon frequency as function of magnetic field, you can see here, this is left-handed and this is right-handed. You can see that there is some splitting, as in the first paper that I show you in the introduction. And we can fit these points with this equation. One part is linear dependent on magnetic field. One part depends on the square of the magnetic field. This is the phonon magnetic moment in the units of the Bohr magneton, right? So you can see here, still not very large, 4.3 times 2 minus 2, but much more larger than the theoretical prediction from 2019 that I showed you also before. And here is the diamagnetic shift. This is the first experimental observation of diamagnetic shift of phonons, which is only possible to measure because of this very particular experimental setup that allows you to apply 30 Tesla, and then you can see this quadratic term. Okay, so in the second part, we now add 10 to the material. So X is not longer equal to 0, right? In this case, we call it observational interplay between phonon chirality and electron band topology. This paper was attract a lot of attention, very high indexes in allometric, top 5% of all research outputs scored by that metric. Okay, published last year. And in this case, there are very strong difference in comparison with only lead telluride. First, we observe two phonons. These are unharmonicity split TO phonons. Let's focus only in the first one. So you can see here that with decrease in temperature, the frequency decreases as before. However, if you continue to decrease the temperature, then frequency increases, right? This one here, blue, is like 8, and then this one is 4.5. So there is a change in the trend for all the samples. Here I'm showing 3 samples, 0.2, 0.4, and more or less 0.6% of tin. Then the frequency of the phonon decreases, but then increases, right? Then you can see here that increases. And this is because with the addition of tin, then the critical temperature for ferroelectric transition can occur here at positive temperatures. For example, for let's say here 0.6 is more or less like 80 Kelvin. Okay, so let's keep the temperature here very low, like 10 Kelvin, so that all the samples will be in the ferroelectric phase, and then apply a magnetic field. So here I have the sample. I put this perpendicular magnetic field, lead tin telluride, different concentrations of tin, linearly polarized terahertz poles, and then I will characterize transmitted terahertz poles, two components, change of polarization which is called Faraday rotation, and change in ellipticity from linear to elliptical. Okay, so this axis is called X. The light is transmitted here through X, and along X, I can see that there is a very large change in all the samples for very high field, here almost 30 Tesla. So they all have a change due to the application of the magnetic field. However, it's more important to note what happened in the perpendicular direction. Here we call Y. So there is a new component. Here there appears EY here in orange. You can see it here. EX, the transmitted along the same direction of incidence, here in black dash line. And also, if I change the polarity of the magnetic field, then EY also changes, becomes the opposite of EY for B. It means that with the application of magnetic field, the phonon becomes chiral, and then the light that was linearly polarized becomes elliptical, right? I can combine these two components, X and Y, like this, EX plus and minus I EY divided by the square root of 2, and then I will call this left-handed or right-handed. Okay, so here I can also take ER and E left and make this combination and calculate complex Faraday rotation. The real part is the Faraday angle, imaginary part is the ellipticity. Let's focus only here in the ellipticity. Ellipticity is much more simpler to understand. It means if we have a circular polarized light, let's say, for example, only EL, then ER is 0, ER is 0, and ellipticity is 1. And the opposite, if we only have right-handed circular polarization, then ellipticity is -1. So let's hear here ellipticity for different magnetic fields, and we see two peaks, one negative peak and one positive peak. So these two peaks correspond to different chiralities. This phonon has one chirality that gives you the negative ellipticity, means it is right-handed, and this one is positive, means that this one here is chiral phonon left-handed. And with magnetic field, you can see that the ellipticity peak changes in frequency, right? Here is much clearer, moves to the increasing magnetic field, decreases the frequency. And if you plot the peak of ellipticity as function of magnetic field, then you can fit it and obtain these three parameters: the frequency of the TO phonon, the phonon magnetic moment, and the diamagnetic shift. And let's look at this one here, which is the most relevant for this talk. You can see here this dashed line is the frontier between trivial and topological phases. And when you increase X, then you see that magnetic moment is very small, but then in the topological phase is very large, right? This for both phonons increases a lot, 2 orders of magnitude. So we can say here that somehow topology enhances phonon magnetic moment. Okay, and in the final 4 minutes of my presentation, I want to show you some future directions. So we start studying thinner films. The films that I show you before are 2 microns thick, so very thick films, very good for the study of phonons. However, we want to know what happened to these phonons, and especially to the interplay between carriers and phonons when we study thinner films. And then we published this paper in Coatings last year for 3 different samples. 100 nanometers, 300 nanometers, and 500 nanometers thick films. What we see here is that thicker films present larger absorption for phonons. For example, if you compare this to this one, and thinner films, for example, this one, the thinnest of all, have this background. You can see here that there is some background at lower frequency. That is much lower here. Here is much more larger. This is Druth conductivity. It means that thinner films have larger carrier density. And in this point is, I think, very nice to show you the capability of this technique. We can calculate fitting here. We can obtain the frequency of the phonon, but also plasma frequency. And from plasma frequency, we can obtain sample concentration if you know effective mass. So here you can also obtain the concentration of the film, and from the width, from this gamma, you can obtain also mobility of carriers. So you can see here in a single measurement, we can characterize carriers and phonons, the frequency of the phonon, width of the phonon, carrier concentration, and mobility. And this is a measurement then of mobility without using any contacts, electrical contacts, which gives you a very clean measurement. Also, in this, if you put these thinner films in magnetic field, we observe cyclotron resonance, as in the paper that I show you at the beginning in the introduction. So this peak here that almost doesn't move is phonon absorption, and then here you can see cyclotron resonance, the absorption from cyclotron resonance in left and right-handed also. And then we want to study two things. First, the dispersion frequency as function of magnetic field for these carriers, and they follow a square root of b function, right? And for both samples, you can see here that for when I move here from this circle to the square, meaning from 500 to 100, this is 500, this is 100, we can see that there is a change in the electron levels that I'm measuring. And also we can study the interaction between these chiral phonons and the cyclotron resonance, right? And it's still not clear what is the effect. It looks like something happened in this crossing, but we still don't know the real effect of this this interaction. Okay, and one point that was discussed in those published papers is the effect of carrier density. When you increase thin concentration to go from trivial to topological phase, you also increase carrier concentration because of the growth. It's something you cannot control. So what we want to do now is to control carrier concentration and carrier type while keeping topological phase. So we are using these samples doped with bismuth. And with bismuth, you can then add in bismuth, you can go from p-type to n-type, and you can decrease carrier concentration and also increase here in the other type. So we want to study this. We start by looking at the ferroelectric transition as a way to characterize if the carrier concentration is changing. And we saw that you can see some change in critical temperature when you increase or decrease the concentration. This is something people know. It had been published that there is a direct relation between critical temperature for ferroelectric transition and carrier concentration. Okay, so I want to finish with this idea then that there is enhanced magnetic phenomena in phonons for non-magnetic TIs. If you want to see more details, you can look at these three publications. There is a lot of theory in those papers. I only focus on experimental part in my talk. We saw high magnetic circular dichroism at lower fields for TCIs, colossal increase of 2 orders of magnitude over insulator samples, trivial insulator samples, and we see also an increase of 1 order of magnitude in the diamagnetic shift. Okay. Thank you for your attention, and we have open positions for postdoc and PhD students. Please check this website where you can find the link for the announcement. Thank you.
Thank you, Felix. Thanks for the very nice talk. There was already a question in the audience that I actually didn't manage to see in time. And Hernandez told us that you answered the question already, but the question was, what is the polarization of the light pulse that is shining on the material to generate the chiral phonons?
Yeah, so the light, we only use linearly polarized light in this experiment, and then the sample transmit circular polarized light. However, it's also possible to illuminate with circular polarized light. You only need quarter wave plate for terahertz. This is also something very curious and I think relevant to say. This field of terahertz technology is very new field, so it's very hard to buy components and to build this kind of experiment really difficult.
Okay. I have a couple of questions, but let me ask the audience if anybody has a question. I'll ask mine later. Anybody wants to ask something? Yeah, there's Sergio Loa has a question. Go ahead, Sergio.
Okay, thank you. Very nice talk, by the way. Really impressive results.
Thank you.
The question I have is, what do you see as the mechanism for the enhanced coupling in the topological regime? Is it through surface states? Is it what is in your mind? What is happening?
Yeah, so this is really still a mystery. One paper that I show here at the very beginning. Where is this? So this PRL from 2021 and this one from 2023, they have some, especially this one from 2021, they explain some mechanism that depends in the gap, in the electronic gap, but it cannot explain the increase after the topological transition. In our paper, there is also some theory based on this PRL, where we apply this PRL to the specific material system. However, it doesn't explain. So far, there is no explanation of why the increase is so large in topological phase. There is only partial agreement in trivial phase. In this case, we are only considering bulk, the topology of the bulk. The surface states are also not included in any theory, current theory. I knew someone will ask this question, so you're seeing here one. I prepared this. this is a presentation in the March meeting. This theory of giant phonon magnetic moment in dope dual semi-metal. So this is the closest theory so far to explain the relation between chirality and topology and how it works.
Okay.
And in this case, they say we show that phonon magnetic moment is linked to Hall conductivity through phonon Hall viscosity. So yeah, I don't know how to explain this.
How to connect that? Yeah.
Yes, and this is not published yet.
I see. Okay. Okay. Thank you.
Okay.
Thank you. Thank you. Yeah, it's a very interesting effect. I have another more mundane question, and that is, how sensitive is your, because you're basically looking at the magnetic moment of the phonons, and I imagine that the mobility of the phonons themselves will play a role in letting you identify, right, where the peaks are, what the broadening is. So how sensitive is the technique to imperfections in the crystal, which are unavoidable, right? So
Yes.
how do you I guess compensate for that or account for that rather?
Yeah, there is some compensation that you need to do between the sample thickness, because normally the thicker the sample, the more perfect it is, and the growth conditions are more, at least for this material, are more stable. And but then light will not go through the sample if it's too thick, and also if it's too metallic. If
Sure.
samples with high carrier concentration are very opaque, are like a metal with microwaves, right? And you don't see anything. Yes. So yeah, there is some limitations in what.
So it's like a tricky intermediate. Right?
Yeah. Yes.
All right. Thank you very much. Very nice talk again. Really enjoyed it.
Okay, thanks, Sergio. Does anybody else have a question? Or wait a second to see. No. Okay, so I have two questions, Felix. One is related. Actually, Sergio stole part of my question, but that's okay. So before going that, let me ask more like a motivational question. So in the beginning, you said that this you can shine light, the phonons rotate, and then generates the magnetic field. So that can be used like a local field. It depends on the spot of the light, but people are talking about applications of local magnetic fields created by these phonons. What is the big motivation behind it?
Yeah, the idea is local magnetic field, right? Then, however, terahertz pulses are very difficult to focus. So typically, we are talking about something like a spot diameter of 3 millimeters.
Okay.
So it's quite large. It's not micro.
Okay. So yeah, not local at all. Okay, thanks. Okay, so the other question was really the same question from Sergio about the origin of these effects in the topological regime. And as we were talking, it reminded me of a paper that doesn't have too many citations. It's a series of papers. I can find it and send it to you. That talks about a thing called separatrix. They call it separatrix. They use this word. I don't know the origin of the word, but it's basically a path on K space. You shine the light, and the electron moves on a path on K space. And essentially, if this path goes through a monopole, goes through a divergence in Berry curvature, what they show is that the absorption of the material, you shine light, electron does this movement, and the absorption of this material, whenever this separatrix theory they have is valid, is huge. So it enhances the absorption drastically. And if you don't have, and if this path doesn't go through the peak of the Barry curvature, then the absorption is much smaller. So basically, they show that you can create charge excitations with a single pulse of light that is highly absorbed. And so the talk reminded me of that. You have now the coupling between the phonons and the electrons, and once you reach the topological regime, you have the Barry curvature. So I don't know if the same type of separatrix idea could apply there. It's not really a question, just to let you know that I'll send you these papers later. There could be something there.
Okay.
The question itself you already answered to Sergio. Thank you. Okay. Any other questions? Anybody? I have one more, but it's in the sense of applications. I don't know if you prepare to answer that. But you were showing that you can replace the magnetic material in the magnetic field to obtain the spin Seebeck effect. Can you explain how these chiral phonons replace those materials? What is the mechanism that allows for this replacement?
Yeah, I really don't know. I just wanted to show you this this example, but let me try to remember how this is.
Just I can read the paper later. Just want to.
I think this is the idea, right? That you can have the spin current is more or less also related to the magnetic field effect, right? That you can have a spin current in the material as a response of this temperature gradient. But exactly how this material works, I really don't know.
It just so I guess the idea is just you break time reversal somehow and allows for one spin to behave different from the other. That's more or less how I understand, but I'm not sure if that's the path, because the chirality depends on the light that you shine, right? So if you shine light, circular polarized light, you excite the phonons with one chirality, or if you shine light with another circular polarization, then the chiral phonons will have a different chirality as well, right? I'm not sure if I get how the chiral phonons are excited on the lower figure. I think that's my question. What defines the chirality in the lower figure?
Well, if the phonons are chiral, then they have different frequency, right? And if you want to excite, then you can only one chirality will absorb the light, because they have different frequencies.
I see. Okay, that's clear now. Okay, guys. So I'll check again if anybody has another question. I guess not. So if not, let's thank the speaker again. Thank you, Felix, for the very nice talk. And that's it. So thank you. We finish it.
Thank you. Bye.